All right, so now we've compared two population proportions, and now we're going to compare two population means, and we're going to learn how to do both the dependent means and also the independent means. But we're going to start with dependent means, also known as paired means, like they're paired with each other. So we're going to talk about the assumptions first. First, you should assume, in order to use this test, that the sample has to be obtained using simple random sampling. The sampled data are matched pairs, which means they have to depend on each other. The differences are normally distributed with no outliers, or the sample size is larger than 30, and that our sample values are independent. So that means that we have to have no more than 5% of the total population can be in our sample. Setting up a null and alternative hypothesis is a little bit different for a paired t-test. We are looking, we're going to set up our null hypothesis. It always has to have the equals sign in it, or some form of an equality statement in it. And this is the difference between the means is equal to 0, or we could say that the difference between the two means is greater than 0, or the difference between the two means is less than 0. And my null, or my alternative hypothesis, the challenge to that is going to be something that doesn't have an equality statement in it. So I could say that the difference between my means is not 0, it's less than 0, or it's greater than 0. So using a calculator for this, you need to know how to enter data into your lists, and you also need to know how to perform an operation in your lists. So we've already learned how to put stuff into list 1 and list 2. So to run this test, you're going to have to be able to subtract what's in list 2 from what's in list 1, and that we're going to store that in list 3. So to do that, you put stuff in data. Oops, hold on. Okay, so now we got my pen under control. So in list 1, you put your data set 1. And then in list 2, you're going to put your second data set. So data set 2. And then you're going to scroll over to list 3. You're going to arrow up until you have the top highlighted, and then you're going to push enter. You know, the little corner button at the bottom. You're going to push enter, and down at the bottom you should have L3, and then the little cursor should be blinking like that down here. When that happens, I want you to push second, hit the 1 button, and down here it's going to say L1. And then you're going to do second. Oh, before you do second, do minus, with the minus sign on your calculator. And then over here you're going to do second, and you're going to hit 2. And down here it's going to say list 2. After you do that, you hit enter. And all your data, list 1 minus list 2, should all pop up in a list next to it. All right, let's try that out. So we have data from 2 car rental companies from 10 different cities, and we are going to check to see if Thrifty is less expensive than Hertz at the 10% level of significance. And notice that this data is approximately normally distributed and has no outliers. So we can go ahead and use a t-test on it. All right. These 2 sets of data are related by the cities. They're matched by city. Okay, so I'm going to go ahead and put the Thrifty data in list 1, the Hertz data in list 2, and then I'm going to go over here to list 3, and I'm going to highlight it. And when I see the little cursor at the highlight this list with the arrow keys, you're going to have L3 down in the corner equals, and that when you highlight, hit enter after you arrow up here, enter, not delete, not clear, your little cursor is going to be blinking, and you're going to do second 1, which is going to be list 1, minus second 2, and then just hit enter. And then a bunch of numbers are going to pop up. You should get 2.82, negative 19.1, negative 2.09, negative 8.01, 0.99, negative 1.03, 0.91, 10.76, 6.82, and 12.5. Okay, isn't that nice? The calculator will do all of that and keep track of it for us. Let's go ahead and set up our hypothesis test now that we have our data in the calculator. Our null hypothesis is that there's no difference in the averages, that they're the same. So my null hypothesis is that it costs the same on average to rent a car from Thrifty as it does from Hertz. So my mean differences are equal to 0. And the alternative hypothesis, the thing I'm testing, is that Thrifty is less expensive than Hertz. So my mean differences are less than 0. Okay, now this is going to be a left tail test, and alpha is 0.1. That's a big alpha, but I guess that's because car rental data really isn't that important. And if I want to find the t-score that I'm going to, for t alpha, I'm checking, I'm going to go to inverse t, 10% is my area, and I have 9 degrees of freedom, because there's 10 of each. I've taken the difference, so I have 9 degrees of freedom. And when I calculate my t-score, I get negative 1.3, oh, no, 83, nope, 38, sorry, just kidding, negative 1.38. Now that I have my test set up, I can go ahead and run my data and see what my test statistic is and my p-value, so I can go ahead and make a decision. And I go over to Stat, Tests. I choose number 2 because I'm going to do just a t-test. So I'm inputting data. When my screen comes up, I'm using data because I have data in my lists, and my mean difference is 0. It's always going to be 0 for a paired t-test. List is going to be list 3. Frequency is 1. And then my test is a left tail test, and I hit calculate. Sorry, my calculator's slow. All right, I get a t-value of 0.089. Oh, that's a positive t-value. And then a p-value of 0.53. Hey, look, my t-value is almost 0. That would be 50% of my data, and I have just over 50%. So my t-value, 0.8, if this were 0 in the middle, it's just to the right of that. That is definitely not in my critical area over here. So going to have to fail to reject that null hypothesis. And my p-value, just for extra verification, 0.53 is definitely greater than 0.1. So this would be a fail to reject. Running out of room. Pretty easy. All right, let's see what happens when we compare two population means that are independent. So we can assume that the samples are obtained using simple random sampling or through a random experiment. The samples are independent. The populations from where we get the samples are drawn are normally distributed, and my sample size is no more than 5% of the population. All right, so when we're setting up our null and alternative hypothesis for independent means, they're a little bit different than the dependent means. They're more like the independent proportions. We're checking mean 1 against mean 2. And the null hypothesis has to have the equality sign. So it could be mean 1 is equal to mean 2, mean 1 is greater than mean 2, or equal to mean 2, or mean 1 is less than or equal to mean 2. And then my alternative is that they're not equal, that mean 1 is less than mean 2, or that mean 1 is greater than mean 2. If you want to calculate the test statistic by hand, be my guest. You have mean 1 minus mean 2 minus mean 1 minus mean 2. That's the average of mean. That's the sample size mean 1 minus mean 2, and this would be the population mean 1 minus mean 2. Whew. Yeah. And then the degrees of freedom are the smaller of your two sample sizes minus 1, whichever one's smaller. Okay, so we are not using pooled t-statistics, and the reason I'm bringing that up is because when you run this on the calculator, we are going to, it's going to prompt you and ask you whether you're using a pooled t-statistic or not, and you're going to say no. All right, so if you have your data, you're going to enter into list 1 and list 2. You don't need a list 3 this time. You are just going to go to a different test even. It's stats, tests, and 2 sample t-test. And you're either going to have data or you're going to have a summary. And we are definitely not pooling. All right, let's go on to an example. Sometimes applicants for a promotion contend that there is discrimination based on age. Conduct a hypothesis test at the 5% significance level in order to test the claim that unsuccessful applicants are from a population with a greater mean age than the mean age of successful applicants. Assume that the 2 samples are independent, simple random samples taken from normally distributed populations. All right, so let's go ahead and set up our hypothesis test. Unsuccessful, we'll call that mean 1. Successful will be mean 2. The null hypothesis is that those means are equal. My alternative or challenge to that is that mean 1, unsuccessful applicants, have a greater mean age. So mean 1 is greater than mean 2. Drawing that out, that's going to be a right tail test. My alpha is 0.05. Now I need to find the T alpha, and I have 24 degrees of freedom because it's 1 less than my smaller sample size. And so I'm going to go to inverse norm, or not inverse norm, but inverse T, and alpha is 0.05, and I have 24 degrees of freedom. So inverse T actually will be very close, or not inverse T, T alpha would be close to Z alpha because I almost have 30. And I get a t-score of 1.71, T alpha. All right, so now I have my test set up. I can go ahead and run the test to figure out what my test statistic is and my p-value is. So I'm going to go into my tests, and I go to stats, tests, and this is an independent mean comparison is done with number 4, the 2 sample t-test. When I choose that, I have the choice of either putting in data or stats. Here I have stats. I don't have data. So I go in, my first mean is 47. My first standard deviation is 7.2. I have 25 people in my sample, and then mean 2, my successful group is 43.9. The standard deviation is 5.9, and I have 25 people in that group as well. And I am doing a right tail test. I'm not pooling it, and I hit calculate, and I get a t-score of 1.67. All right, 1.67, even though it's almost 1.71, is in this region. And so that is close to 1.71. My p-score, or p-value, sorry, not a score, is 0.051. P is slightly greater than alpha. That means that I'm going to fail to reject. It looks like that the average age of unsuccessful applicants for a job or promotion have a greater or a higher average age, or don't have a higher average age. All right, both of these, the test statistic and the p-value, indicate that. All right, let's do one more example, and then we'll call it a day. BMI for Miss America, the trend of thinner Miss America winners has generated charges that the contest encourages unhealthy diet habits among young women. Listed below are body mass indexes for Miss America winners from 2 different time periods. Consider the listed values to be simple random samples selected from larger populations. Use the 5% significance level to test the claim that recent winners have a lower BMI than winners from the 1920s and the 1930s. So these are going to be my first mean, these are my second means, and I am going to set up my tests. So my null hypothesis is that mean 1 equals mean 2. And then my alternative hypothesis is going to be, let's see, we're testing that recent winners have lower. So mean 1 is less than mean 2. All right, that is going to be a left tail test. And I'm using a alpha of 0.05. So T alpha is going to be inverse T, 0.05, comma, and then my degrees of freedom for this are my data from list 1, or the data from both the lists minus 2. So I have 10 pieces of data in each list. Minus 2 is going to be 18 degrees of freedom. And that gives me a T alpha of negative 1.73. All right, I'm ready to run my test. I'm all set up. I go into stats, tests, two sample t-test because these are independent, right? My winners don't really have anything to do with each other. And then I go to data this time because I have data in my lists. And so I'm choosing data. And then in list 1, I'm going to just type list 1, list 2, frequency 1, frequency 2, 2. I'm going to choose a left tail test. I'm not pulling it, and calculate. I get a t-value, or a test statistic, of negative 2.33 and a p-value of 0.016. And then I'm going to check now. Negative 2.33 is less than negative 1.73. It's in that critical region. And when I double check p against alpha, 0.016, my p-value, is less than 0.05. So I'm going to reject the null hypothesis. So what that says is that the body mass from recent years is less than the winners from 1920s. All right, hopefully that is all clear for you, and we will practice in class.